Good afternoon, everybody, or good evening, wherever you are. Thank you so much for joining us for another session of EI Live K-12 for students and educators and families. My name is Cassie, and I oversee educational and outreach activities at the Earth Institute. And so for those of you who might be joining us for the first time and aren't familiar with the Earth Institute, just to give you a little bit of some background, our core mission is to foster a greater understanding of the science behind the climate crisis, but perhaps more importantly, what we as global citizens can do. Experts that make up the Earth Institute include economists, business and policy experts, public health experts, specialists in business and law, and most importantly, our earth scientists, our earth and environmental scientists. The Institute is actually made up of more than 24 or so research centers, and hundreds of people who collaborate across many different disciplines and across departments at Columbia University. What we're hoping to do with these EI Live K-12 sessions is to bring our science to you in a very interdisciplinary way through our experts. We are going to have these sessions until the end of June. All the remaining sessions are on Thursday afternoons at 4 p.m. Eastern Standard Time. And if you would like any additional information about any of those upcoming sessions, feel free to get in touch with me directly. Today, we're really lucky to have Dr. Vicki Ferrini from Lamont-Doherty Earth Observatory. Lamont is the largest research center that's part of the Earth Institute, and she's going to be speaking to us about her work, which has been focused around ocean exploration and how she's using different technologies to map very deep parts of the ocean that we physically cannot get to. So she's going to go through her presentation, and then we also have a colleague from NASA's Goddard Institute of Space Studies who's going to join us a little bit later on to share some NASA resources as well with you. So Vicki, whenever you're ready, if you want to take it away.
Awesome, thank you. Let's see. Just share my slides. Okay, that looks good.
Yep.
Okay, great. So I am going to talk to you today about how we explore Earth's final frontier, the very, very hard to reach deep sea. So to get started, the Earth, this beautiful blue ball that we're on, the ocean covers about 70% of this planet that we're on. And that means that the majority of the planet cannot be seen. So the ocean really hides this vast underwater region from us. And while we'd like to be able to drain the water away, like what happens when the tide goes out, this is a picture from the Bay of Fundy in Canada. This is high tide and this is low tide. We can't drain the ocean's waters away to see what the seafloor looks like underneath. So we have to use a bunch of different kinds of technology to be able to see and explore and understand these hidden undersea environments. So when we look at a map of the planet, you get a little bit of a sense of the shape of the seafloor, as is depicted here. You can tell that in the middle of the Atlantic, for example, it gets a little bit shallower. So there's the mid-ocean ridge here. And you can see some crude shapes, but really this is not based on very much data at all. So if we try to think about how little of our planet and how little of our ocean is mapped, we can take this map of the planet, consider that the whole planet 100%. If about 70% of it is water, that's covered the red area here. And if only about 20% of the planet of the ocean has been mapped, that's this blue box. So there's a huge amount of the ocean and the planet that we really just haven't seen and haven't explored. So most of what we know about the shape of the sea floor is based on prediction, based on satellite data. And so the way that this works is that we're using information from satellites that give us measurements of the shape or the height of the sea surface, which responds to the shape of the seafloor very, very slightly. And we're able to use that information to compute, oops, that didn't work. To compute what the height of the seafloor is based on gravity. So the nice thing about this technology is that it gives us a complete picture of the planet, but it's not very detailed. And so if we consider what that would be like, if you look in Google Earth, look at a map of New York and look at the United Nations building, this image is about 1 meter resolution. You can see lots of details. If we considered what this would look like with the baseline of resolution in the ocean, the kind of data that we have, it would look like this. You'd see almost no detail at all. So this is the kind of information, this is how much detail we can see about the majority of the planet. So how do we actually see through the water? Since we can't see very far through the water, what do we do? In the old days, what was done was something called lead line measurements. So a weight on a rope or a wire was put over the side of the boat. You might do it if you're floating around in a kayak. You can put the oar over the side of the boat and get an idea physically of what the distance to the seafloor is. But now we use sound. So we measure the time it takes for sound to go from the ship to the seafloor. We can compute distance based on that time. So about 100 years ago, this started to get used where we could just measure directly under the ship. Kind of think of it like a flashlight looking down. You just collect a measurement as you go. Now we're using something called multi-beam sonar, which gives us a whole bunch of these sound beams together. And again, with this flashlight analogy, think about the seafloor as this dark area that we can't see. So if we have one flashlight, we can see a little bit of area. If we put a whole bunch of flashlights together, we can see a lot of area at the same time. So we're able to collect lots of sound measurements and compute what the shape of the seafloor looks like. So that has allowed us to move these old nautical charts. This is the old way that people used to look at what the shape of the seafloor looked like. And now we can see it with much more detail. We can see the little bumps and wiggles and really understand more what this looks like. The colors here look like candy, but the red is shallower and the blue is deeper. You'll see that in a bunch of these images. It helps our eye better understand what we're looking at. So these kinds of instruments can be big, they can be small, they can be on big ships, small platforms, little robots. They all work kind of the same way. They give us this information, the sound measurements, and we have to monitor the movement of the boats and things, and we can put all this together to get these beautiful maps of the seafloor. So what does this actually do to our maps? How does it compare to the prediction? Well, this image on the left shows what predicted bathymetry looks like based on that satellite measurement in a 50 by 50 kilometer box. So you really can't see too much detail. If you actually come over the same area with a sonar system, you can suddenly see lots and lots of detail, almost like you can see the landscape as you're looking out from a hill, but in this case, or down from a plane, right? You can see all the shapes of the landform. Here's another example, very fuzzy, hard to understand what we're looking at, suddenly much more detail. And my last, perhaps favorite example, if you watch right up here where this profile is, once the sonar comes through, you'll see it come through here, it maps this little mile tall hill that was just not there before. We had no idea it was there. So as we collect more and more data, we start to see the seafloor with more detail and start to really understand these beautiful landforms that are hidden from us by the water. What does it look like when we're collecting the data? Well, it might not be too exciting for lots of people, but it looks like this. I think it's really exciting. Every time this changes, we're seeing another ping of sound, another transmission of pulse of sound, and it gives us this profile of depth data underneath the ship as it moves along. As I said before, the ships move a lot, as you can imagine, when the waves are out there, we're getting bounced around. And so it's really important that we monitor the motion of the vessel so that we can put all those individual measurements of distance in the right context, and we don't get these weird patterns that obscure these beautiful detailed images that we can create. And when I say that the ships can move a lot, I mean they can really move a lot. Here's a picture from above deck as one of the ships is cruising along on a fairly rough day. It's exciting, it can be a little scary, but mostly it's exciting when you're out in the middle of the ocean. This is I have a couple examples of what it's like. This is in the galley of one of the boats. and the wave just splashes right up against the window. Again, sometimes a little scary, but mostly exciting. And here's one of my other favorites. I was sitting, collecting data, just kind of minding my business, and my soda can just slid right off the table because of the motion of the ship. So with this technology, it lets us basically start to move the water out of the way. Here's an example from the South Pacific. This is a new island that formed. We were able to go and map around it and to really try to see what was under the water. And with that new data, we could see that this new island formed on top of a big underwater volcano. We can see all sorts of details here. You can see that there's a big rim. This is the caldera of the volcano. There's these big downhill sloping valleys of sort. You can see all kinds of motion and lava formations. And it's pretty exciting once you can reveal this information. Here's another example from the deep South Atlantic. We're in about 5,000 meters of water, which is about 3 miles. And these ripples that look just like the ripples you might see when you go to the beach are actually on the order of 100 meters tall, some of them, which is the size of a football field. So these features can be enormous. And with this kind of technology on ships, we can start to see the very basic shapes of the seafloor to better understand what's down there. Once we have these maps, it opens the door for all kinds of further exploration. So we can use all different kinds of robots, submersibles, and other kinds of platforms to get close to the seafloor to see with our own eyes and with cameras and other sensors, the details of what's down there. So what you see here in the top couple of images, this is the submersible Alvin that you may have heard of. This is a remote operated vehicle called Ropos. They both get lowered off the back of the ship. Alvin is free swimming and it goes off with people inside and does its work. Ropos and other ROVs, there's another one shown here on the bottom, remain attached to the ship, and it's like a remote operated vehicle, right? So there's a controller and a pilot on board that's telling the vehicle where to go, and it's sending data up to the ship in real time, and we can watch it and make decisions as a group instead of just the few people that are inside the submarine. There's other vehicles like these ones on the bottom that are autonomous. They work kind of like a Roomba if you have one of those or if you've seen those. They go off, we tell them what to do, but they go off on their own. They collect their data and they come back with it. We bring them back on board and we download the data, and then we can analyze it and use it to plan future expeditions and future missions. So a little bit about Alvin. It's a really exciting submersible. I've been down in it a couple of times. I work a lot with the data that it collects, and it's the only deep diving submersible with this kind of capability in the US for the academic research. It takes, the depth capabilities are one of its unique features, but also the fact that it can take 2 scientists at the same time and 1 pilot is another exciting and unique feature, because more scientists in the submarine is very helpful when you're trying to make decisions as you're down there. Alvin and the remote operated vehicles have manipulators that are like hands. You can see them here on the front. And this little basket here is where samples get put in as they're collected on the seafloor. Once you get down to the seafloor and you're in Alvin, you can look out the window and see with your own eyes what the seafloor looks like, which is amazing. And you can work with the pilot who will control these manipulators to collect samples, physical rocks, maybe organisms, sometimes water samples. It's a really, really exciting experience. With these other vehicles like Jason, the remote operated vehicle, we're using cameras, video cameras as our eyes basically on the seafloor. And it helps us do whatever work we need to do, also with manipulators and baskets for storage and bringing samples back and forth up to the surface. I like to think of these both as kind of looking through a straw, because underwater you can't see very far. The light scatters very quickly. You can't see too far ahead of you. It's very dark. There's a lot of pressure there, so it's a very hostile environment. It's a really exciting and unique opportunity to get there physically, but with cameras and data coming back up in real time, this experience can be shared with lots more people, which is a very exciting modern evolution of this stuff. So what does the seafloor look like? Here's a picture of lava that's been formed there. It's got some sediment on top of it, so it's not particularly fresh. But we can make some observations about the geology, put this in context with the other data that we have, and start to piece together a more complete understanding of what's happening in these various environments that we visit. Here's another example of a hydrothermal vent where there's hot mineral-rich water coming out of the seafloor. It forms these deposits that can be full of minerals as well. And there are organisms that live at these environments, which are really toxic in many ways and lots of pressure, and they're adapted to live there, and they're beautiful and spectacular and offer all kinds of important insight about how life formed, how life has evolved, and you know, various new things that we can apply to everyday life, from genetic sequencing to understanding how we can take advantage of various resources and minerals in the sea, etc. So another exciting thing for me, since I specialize in mapping, is that again, if we think about the flashlight analogy, when you have a surface vessel, it has sort of big flashlights pulled far away from the wall. It's a broad light that's shining against the wall, or in this case, the seafloor, giving us a crude, rough idea of what the shape of the seafloor looks like. But when we have these vehicles that can get down close to the seafloor, it's like we can bring those little flashlights much closer and we can see much more detail. So with the same kind of technology that we use to create the base maps that we have to do before we can get down there with the vehicles, with this technology on the vehicles, we can collect very, very detailed maps of the shape of the seafloor. So this looks very much similar to the maps I showed you before, but there's a lot more detail. At this scale, the mesh that we sort of use to make this visualization is less than a meter in resolution, so it's pretty small. You could actually see the chair that I'm sitting on with this kind of resolution, whereas with the ship-based example, you might be able to see a plane if you're in shallow water, but you wouldn't really be able to. So a lot more detail. And so when we combine this information with optical camera, photographs, etc., we can start to really understand what we're looking at here. So this lava, similar to what I showed you before, is why this texture looks all bumpy. And these things that are sticking up are big hydrothermal vents that have organisms and communities and all kinds of interesting structure. And so by putting this together, we can start to get a sense of what it's like to be there ourselves and what it looks like. This is just to show you the size of this kind of feature, which is hard to really understand. What I did is I stacked the size of a person, assuming about 6 feet tall. So if we were standing on the seafloor looking at this hydrothermal vent, it would be about that big relative to what we're used to. So it's small, it's detailed, but it's also really big. It's a really interesting sort of aspect to this work. So with this kind of technology, we can now do what was almost unthinkable a couple of decades ago. Back then, we could describe what we saw and provide some isolated pictures to artists who could help draw what this looks like and help us communicate it to the world. And now we can use data. This is the same place. To actually show the shape with great detail of the seafloor and really start to contextualize, really start to understand, you know, this environment that we could otherwise really not see ourselves. One other exciting development in this space is that with lots and lots of pictures, you can put them together and create what it would look like as though you were there with your own eyes. So we wouldn't be able to see this very easily at all if we stood on the seafloor, because we wouldn't be able to see so far. But by putting together lots and lots and lots of pictures, we can start to visualize what the shape and details of these features are like. So one other really exciting thing that happens now is that the technology exists so that when operations are underway in the deep sea using these kinds of vehicles, not only is the data and the action sent in real time back up to the ship where people are controlling what's happening and making decisions. But that information is also able to be sent back to shore. And so people can tune in live during dives of various remote operated vehicles. You can be part of the expedition in a way and watch what's happening and hear the dialogue that's underway. And it's really helping to make this experience and this data more accessible, not just to the science community, but also to students and the world at large. So there's lots and lots of ways to engage. You can not only watch this as it's playing out, but there's different interfaces where you can go and explore the data and sort of discover on your own new and exciting things in video and in images. And there's lots and lots of resources that are being put out to help people better participate, I would say, in this really exciting world of ocean exploration. So I just wanted to close with a little more context, a little more information about how little of the ocean is mapped. So if you look at this view of the planet, you can see that most of the ocean is covered in black, and some little bits of it here and there, some larger regions. Certainly some places are fairly well shown in different shades of blue that indicate the depth, but the majority of the ocean is still black. And so this is a way to help understand where the gaps in data coverage are and how little we really know about the shape of the seafloor and what's down there. And so as we work to map this planet and as we work to map the ocean, we have no idea what we're going to discover. There's lots and lots to learn. There's lots to discover, from ecosystems and organisms to resources to shipwrecks, all sorts of things. And so as technology has gotten us here and as the world comes together to explore and map the ocean, we will discover unimaginable things. And it's a really exciting time to be in the world of ocean exploration. And I'm going to stop there with this beautiful picture of an underwater organism. And just to remind everyone that exploration is a wonderful way to be reminded of the beauty of the world and to inspire us to learn more about it and to focus on taking care of it for ourselves and for future generations.
That's a great way to end. Thank you, Vicki. Okay, so we have a couple of questions in the Q&A box. Vicki, if you want to take a look, that would be great. And Rosalba is here from NASA GIST, and she's going to share a couple of undersea and ocean-related resources from NASA. And for our viewers, if you do have questions, feel free to continue typing those into the Q&A box, and we will get to those shortly after Rosalba finishes with her resources. Rosalba, if you want to go ahead.
Google document that
Can you hear me?
just included a link to.
Yes, but we're also hearing other something else on your screen.
Yeah, I don't know what is happening with my computer. Give me just 1 minute.
Yeah.
Teachers to just skim through.
Maybe you can go over the questions while I fix my issue with my computer.
Read it more carefully.
All right, so Vicki, I think you've addressed one of these already, which is that the sort of black spots on the map. Oh, yes. Okay, great. Yeah, where there is no data. So yes.
I can add a little bit about that.
Yeah.
So there's a big international effort to bring together all the data that exists.
Okay.
And that map shows the data that's been integrated so far. And we're working on all the publicly available data. And part of this effort is to bring everyone who has data together to figure out how they can share it. So there is more data than that.
Okay.
And it will fill in, I think, more and more quickly as time goes on.
Yeah, fantastic. Great. So Jenny has asked about what you see on the ocean floor, and specifically if you could see plastics, because as we know, plastic pollution is a very big concern, particularly in oceans. So yeah, curious if you see any of these of this evidence of the pollution.
Yeah, sometimes we do see it. I think there was a plastic bag that was observed in the Marianas Trench not so long ago. It is there. Personally, I've seen soda cans occasionally that were probably thrown over the side of a ship. I think a lot of the plastic in the ocean is in very fine little particles, but there are big pieces too. And hopefully we can move away from so much plastic and so much plastic polluting the ocean, but it is there.
For sure. Yeah. George had a question, I guess, because you were talking about lava and, you know, whether or not you've seen if volcanoes do actually erupt underwater, and if so, what could that look like?
So yes, they do erupt, of course. There have been a few underwater eruptions that have been fairly well documented. One of them was in the 90s, where it was after the eruption, scientists went to the site and found evidence of it. That was one of the first where there was data documenting before and after the eruption. That particular site, which is the East Pacific Rise, which is the first place that I dove in Alvin, actually, erupted again in around 2005. There was some evidence in micro earthquakes that there was an eruption coming, and it did happen. The assets, the robots were not on the seafloor when it happened, but again, it was documented soon after the eruption. There have been other eruptions at other locations. I would say the technology and the data that's being collected is improving to the point that it's getting easier to anticipate when this might happen. It sort of does a reset of the ecosystem, which is a whole other interesting thing that happens. When the lava is fresh, it looks very black and shiny often. So that sort of sediment that you see on top of the pictures I showed you wouldn't be there. That's one of the ways we can guess how fresh it is.
Great. Thank you. Someone has asked how we can tune in live to some of the sort of dives.
So there are two different programs here in the US that are very popular for this. Nautilus Live. So the Ocean Exploration Trust runs the Nautilus research vessel. And so Nautilus Live does a lot of live broadcasts. And the NOAA Office of Ocean Exploration and Research also does a lot with their vessel, which is now the Okeanos Explorer. So if you look at either of their websites, I can try to find them after the camera's off and put them in the chat.
I've got the Nautilus one live.
Awesome,
Yeah.
perfect. Yeah, so they do a lot of live broadcasting. Schmidt Ocean Institute also does, and they'll announce it on Twitter and other places, Facebook, so you can kind of keep your finger on the pulse that way.
Yeah, fantastic. Great. I'm going to go to one more question, and then we're going to turn it back to Rosalba. Another question from Jenny. This is actually a really great question of whether or not the mapping impacts ocean animals. And this is really, we get questions as well, because we've also had scientists talk about how they tag animals in Antarctica. And it's always, it's such a great reminder that we are also thinking about all these animals, all this life that exists in places. And so Jenny, thank you for your question, and thank you for caring about the animals. So Vicki, what?
So the general thinking and the basics of sort of how physics and sound underwater works is that high frequency sound doesn't travel very far. It gets scattered. So when we're mapping with high frequency sound close to the seafloor, getting those very detailed maps, we sort of operate under the assumption that we're not disturbing too many things. A lot of sonars are used to look at organisms in the water column. So like on my little boat, I have a fish finder and I can see the fish underneath. They generally don't scatter. There's, I think, some sensitivity to some different frequencies or concern about sensitivity, particularly the lower frequency, which will travel further. And so on the research vessel that we operate at Lamont, for example, which uses very low frequency sound to look below the seafloor, they always bring on board some specialists who keep an eye out for marine mammals and birds. And if they see them anywhere nearby, they stop operations out of an abundance of caution so as not to disturb these organisms.
That's great. All right, thank you. And we have a couple more questions. So Rosalba, I'm going to turn to you, and then Vicki, we can come back to you, and then you can answer some of those as well.
Great.
thanks.
Thank you, Cassie. Sorry about my technical difficulties. Let me share my screen. You hear me okay now?
Yes, perfectly. Thank you.
Yes, great.
Yep, and I see.
Awesome. And you can see my screen?
Yeah.
Okay. So yes, thank you, Cassie. My name is Rosalba. I help support NASA's Office of STEM Engagement at the Goddard Institute for Space Studies. And yeah, I am very grateful for the opportunity to share a few supplemental resources just for further exploration. I'm going to share the links to these resources on the chat. So yeah, I want to share about Ocean Worlds, the scientific visualization studio, and I also want to highlight a video from NASA's astrobiology program. So the first resource, Ocean Worlds, it's a pretty beautiful website that lets you explore information not just about our oceans, but also about oceans in other parts of the universe. So for example, you can explore questions such as how water arrived on Earth, how it originated, how we monitor our own oceans, and also which other worlds in our solar system have their own oceans. So again, it's a very beautiful website, so I do encourage you to explore it. The next resource is the Scientific Visualization Studio. So here we have a team working very closely with scientists to create these visualizations and animations and videos and images that can help us understand Earth science and space science better. And so the video that I sent the link for specifically, it's a visualization of the draining of the Earth's oceans. So it simulates an incremental drop of 10 meters of the water's level on Earth's surface. And so you can see, you can visualize underwater mountain ranges and trenches. So it's a pretty cool visual. But the Scientific Visualization Studio has thousands of visualizations and videos that you can download for free. So it's a pretty cool resource that I also suggest for you to explore. And last, I just wanted to highlight this video from NASA's Jet Propulsion Laboratory. So it is about underwater white smoke events. And the idea here is that we have many scientists that believe that for NASA to, or other scientists to do exploration about life in other worlds, right, in other planets, that we should start by understanding how life started on Earth. And many of them believe that it started at the bottom of the ocean. So on this video, they showed you how they mimicked these undersea environments. And they show that under extreme pressure, the fluids from the seafloor cracks mixed with ancient ocean water could have produced the first building blocks of most of the life on Earth. So it's a pretty cool video. So I also suggest for you to check it out. And yeah, that's it for me today. Thank you.
Thank you, Rosalba. Right. And this is good timing here. Maybe Vicki wants to answer this question live, which is describing what a descent in the Alvin feels like for someone who's fairly afraid of anything beyond a pool. This seeing your image of Alvin descending sort of into darkness looks very scary, but if you could tell us what it's like to be in it.
Yeah, so when I dove in Alvin, it was before it sort of had a bit of a facelift, if you will. It's a little bit different now, but basically the heart of where the people and the electronics go is a titanium sphere that can withstand the pressure, because there's massive pressure at the bottom of the seafloor. At the bottom of the ocean. So it's a sphere that has all the life support stuff. So there's oxygen for you and all the electronics and computer screens, and there's space for the 3 people. When I dove, it was a little bit smaller than it is now, I'm pretty sure. You know, your legs might you know, kind of wrap into the other person's legs, particularly when you're looking out the window and all excited. But you go in your socks and you wear warm clothes because it gets chilly down there. The cold temperature of the ocean. Someone asked what the temperature is like. It's about 3.5 degrees Celsius. It's cold. There's a density reason. Water is most dense at 3.5 to 4 degrees Celsius. So that's why that's the temperature at the bottom of the ocean. But that cold can kind of sort of seep in a little bit over time, just because the whole thing is getting chilled. But it's really exciting. In some ways, it's like going in an airplane, you know, you're going into a place that you're not used to being, and someone else is the pilot and is responsible for your safety. Just like in an airplane, there's oxygen for emergency purposes. You have to get fitted with an oxygen mask before you go so that they know it'll fit should it be necessary. It's of course not been necessary, but one of the interesting things and a challenge of the group that runs that vehicle is they have to be very concerned with everyone's safety. And so they do a lot of work to make sure that it's safe for people, and that we can do the work that we try to do with it. So it adds a whole other level of effort for them to really do that. And there's a lot of certification and checking and all that. You go down, you take a lunch with you, you're down for less than 8 hours, typically, because they limit the time on bottom based on how long they want you in the water, based on oxygen and stuff that's available. Of course, there's more than 8 hours of oxygen, but they want to make sure that basically you dive just during the day. They put it in when it's light out, they bring it out when there's light out. It's really, really exciting. Like, you kind of forget the fear because it's so exciting. And when you can look out the window and see the two worms at almost arm's length, there's nothing quite like that experience. And for me too, the first time I dove, it completely changed my understanding of the data that I'd been working with. So looking with my own eyes really changed my whole experience and understanding. So it's amazing.
Awesome. Yeah, and you sort of answered half of this question, which was the next question, which was sort of how long a dive in Alpha could be. So it sounds like you take food with you because you're down there for
lunch,
at least a couple of hours, and for lunch.
Spend lunch down. I mean, it depends on the water depth. So the time it takes to get down and the time it takes to get up is different in deeper water than in shallow water. But generally you go in right after breakfast and you come up by dinner. Yeah.
Yeah, not a bad way to spend a day.
Absolutely.
And I guess the second part to this is it considered a submarine?
Yes.
Yes. Okay. All right. That's a great question, because I was, you know, what makes a submarine? And because this is a manned sort of vehicle. So
yep. So it's called sometimes a submarine. It's sometimes called a submersible. It's sometimes called an HOV for human occupied vehicle.
Okay.
But it's a really, I should also, one of the things that we do with these vehicles is we take styrofoam cups or styrofoam wig heads, and we draw on them. And then we attach them to the outside of the vehicles and take them to the bottom of the ocean, and the air gets squeezed out by all that pressure and the cup gets shrunken.
That's what it looks like. Wow, that's pretty cool.
Yes, not, generally we don't like to use styrofoam, but this is one case where
for science,
everybody gets excited.
No, that's great. Thank you for sharing that. The question about sort of if you're wearing fins, how long might it take you to dive from the surface of the ocean to the deepest part of the sea? I don't even know if this is possible, but and what material might be able to withstand that type of pressure?
So you couldn't dive as a human not enclosed in something that is resistant to the pressure. I know that there are a few submersibles and submarines that, well, certainly there's a lot, right? There's military ones too, but the ones that are used for science and exploration are all pretty small. I believe titanium is part of it. I don't know what all the materials are made of, but basically everything that goes down on these vehicles, every sensor that gets put on the side, every system that gets mounted on it has to be pressure tested as well, because we don't want a camera and its pressure casing that it's in to implode and potentially disrupt or damage the vehicle while it's underwater doing its operations. Some of the acoustic transponders that are used to help support operations with these vehicles are in, I think they're glass balls that are encased in other things, and those are put down. It's really, I mean, the windows of Alvin are very, very thick glass. So there's different things to help manage the pressure, and everything is very precisely engineered and carefully managed to make sure that it's safe and it doesn't implode, though accidents have certainly happened in the past with some things.
Yeah. Yeah, and the next question is sort of follow up on that is Alvin made of those materials that you just mentioned?
Believe so. I haven't kept up completely on what the latest materials being used are, but there's foam, syntactic foam in some cases involved. There's various things. A lot of what has to be done is, you know, the vehicle descends with weights, and then it can cast some of those weights off and just leave them on the seafloor. And then it has to be neutrally buoyant so it doesn't start to rise until it's ready for it to start to rise. So there's additional weights that are left at the bottom so it can come back up to the surface. So there's a lot of very, very interesting engineering that goes into making all this work. So it's a really great intersection of science and engineering that makes all this happen.
Yeah, and that's a great, I think that's a great reminder, and I think that's a good sort of place to wrap up. And I'm, from my own interest, and I'm going to sneak in a question in here. You know, what are the sort of emerging technologies that that you're learning about, that are perhaps you're going to get to experience in the near future? I mean, technology is just evolving so quickly in so many different places, and it's great that you've touched on sort of the engineering, technology, and earth science intersections. So yeah, do you know of any, you know, cool upgrades to Alvin or other
Yeah, I mean, one of the really exciting things with Alvin and other vehicles like it is there's always emerging technology, new sensors that scientists are bringing to bear, or our scientists are working with engineers because they have a particular need to measure new things or measure them differently. So there's always new technology coming. A lot of what I'm excited to see happening now is increasing autonomy. So those assets, both underwater and on the surface of the ocean, that can be programmed to go out and collect data. They can do things more efficiently if they have enough battery and capacity to be out there. We don't have to have, you know, the big research vessel with 50 people on board sitting, sort of babysitting a particular asset. We can have a bunch of things working together at the same time. So there's a lot happening in that space, and there's a lot of exciting stuff happening in the data space, which is where I like to sit. So really bringing the data together, making it more accessible, running new algorithms to learn more from the data faster. I think we're going to see a lot of things happening in that space in the next few years.
Awesome. Exciting things to keep an eye out for. Well, thank you so much for that. Do you have any further comments for our viewers? Any additional thoughts?
Maybe just, you know, if you're interested in this kind of stuff, there's a lot of information out there. I think the community is getting a little bit better about making information more accessible and about trying to engage and bring people along on this exciting journey. So don't be shy, find what interests you, and you're going to find all kinds of interesting material to engage with.
Yeah, fantastic. Well, thank you so much for your time, and thanks to our viewers for joining in. We will be sure to share all the links that Rosalba shared and any additional links that Vicki mentioned where you can catch a live dive. And we'll share the recording of this video as well. Thank you for tuning in for another session of YA Live K-12, and we hope to see you in the future. Thanks again, Vicki.
Thank you. Take care.
Bye, everyone. Bye-bye.